Hello everyone, welcome to the 21st lecture on general topology. In the last two lectures we have discussed about compact spaces. In this lecture we'll discuss about some variants of compact space. The first variant of compact space is limit point compact. A topological space X is said to be limit point compact if every infinite subset of X has a limit point. In the case of compact space definition, we know that a space is said to be compact if every open covering of X has a finite subcollection which covers the space. But in case of limit point compact, we are saying a topological space X is said to be limit point compact if every infinite subset of X has a limit point. Then the question arises, what is the relationship between limit point compact and compact? Now the statement is every compact space is limit point compact. Now let us prove how every compact space is limit point compact. Let X be a topological space which is compact. Now we have to prove that the space is limit point compact. To prove X is limit point compact, let us take an infinite subset of X. Let A be a infinite subset of X. Now we have to prove that A has a limit point. So we have to prove that A has a limit point. Now let us assume that A doesn't have a limit point. Suppose A has no limit point. Since there doesn't exist any limit point of A outside it, A is closed. Because in the definition of closed sets, we know that a set is closed if it contains all its limit points. Here A has no limit points. That means A doesn't have any limit point outside A. So we can say that A contains all its limit points inside it. That means A contains all its limit points because A doesn't have any limit point outside A. So A is closed. Since there doesn't exist any limit point of A outside it, A is closed. Also, points inside A are not limit points of A because A has no limit point. So for every A in A, there exists an open set UA containing the point A such that UA intersects A at only one point, that is A itself. Since A is a point in A and we have said that there is no limit point of A inside A, so this A is not a limit point of A. And we know that from the definition of limit point, a point is a limit point if every open set containing that point intersects the set. Here this point A is not a limit point of A. So there exists an open set. There exists an open set which doesn't intersect A at any point other than A. So there exists, since A is a point in A, there exists an open set UA containing A which intersects A only at one point, that is A itself, because A is not a limit point of A. Now we have taken every A in A. If you collect all such UAs for every A, then this collection UA for every A belongs to A is an open covering of A by sets open in X. Since A is a closed subset of X and X is compact, A is compact because we know that closed subset of a compact space is compact. Since A is closed subset of a compact space X, A is compact. Thus, the open covering U has a finite subcollection V which covers A. Because U is an open covering of the compact set A, so U has a finite subcollection which covers A. Let that finite subcollection be V. Since A is covered by a finite subcollection where each element of this V is an open set UA which contains a single point A is finite. Since this V is a finite subcollection and this V contains sets like UA and that UA contains only a single point A. So this finite subcollection contains finite number of elements and each element contains a single point. So A is finite because this B covers A, which is a contradiction because we have taken that A is an infinite set. This contradicts the fact that A is an infinite subset of X. So our assumption is wrong. We have assumed that A has no limit point. So our assumption A has no limit point is wrong. Therefore, A has a limit point. This proves that every compact space is limit point compact. Now here we have an example of a limit point compact space which is not compact. Let us consider the set Y containing 2 points A, B with indiscrete topology. And in the case of indiscrete topology, we know that here the only open sets are empty set and the whole space. And let take another set X, which is set of positive integers. So now we have with us two sets. X is set of positive integers and Y is a 2-point set having indiscrete topology. Now let us consider the product space X cross Y. X is set of positive integers and Y is a 2-point set containing 2 points A and B having indiscrete topology. Take the product space of X cross Y. Since Y is having indiscrete topology, only open sets in Y are empty set phi and Y. Thus, any subset of the product space X cross Y which contains the point NA will have a limit point NB. We know from the product topology that the basic open sets of X cross Y are of the form U cross B, where U is an open set in X and B is an open set in Y. But in the case of open sets of Y, we have only two open sets, empty set and the whole space Y, because Y is having indiscrete topology. So any basic open set of X cross Y is of the form of U cross B. Here we are saying that if NA belongs to a set, this ordered pair NA belongs to a set, then this NB point will become a limit point of this set containing NA. Because any set, any open set which contains this point NB will intersect the set which contains the point NA, because the Y is having indiscrete topology. U cross B. B always contains, either B is empty or B contains both the points A and B. So wherever B appears, A will be there in an open set. So here we can say that any subset of the product space X cross Y which contains the point NA will have a limit point NB. And the reason is every open set containing NB contains the point NA. So if the subset A of X cross Y contains NA, then NB is a limit point of A. Similarly, if the subset A contains NB, then NA is a limit point of A. Hence, every subset of X cross Y has a limit point. So, X cross Y is limit point compact. So, here we have proved that the product space X cross Y is limit point compact, but the product space is not compact. Why it is not compact? Because the collection of open sets N cross Y, where this N is a set of is a member of the set of positive integer. This collection is an open covering of X cross Y. But this open cover doesn't have a finite subcollection which covers X cross Y. So X cross Y is not compact. So here we have shown an example in which a space is limit point compact but not compact. One more variant of compactness is sequentially compact. A topological space X is said to be sequentially compact if every sequence of points of X has a convergent subsequence. One more variant of compactness is locally compact. A topological space X is said to be locally compact at a point X if there exists a compact subspace K of X such that K contains an open neighborhood around that point. That means a space X is said to be locally compact at a point X if there exists a compact subspace K of X such that K contains an open neighborhood around X. Suppose here we have the topological space X and here we have the point X. Now this space is said to be locally compact at this point X if there exists a compact subspace K. There exists a compact subspace K such that this K contains an open neighborhood around X. And a space X is said to be locally compact if it is locally compact at each of its points. Now the relationship between compactness and locally compactness is every compact space is locally compact. This we can prove in this way. If X is a compact space, then if we take any point X in X, then we can have K as the whole space X. So for every point, the space itself serves as a compact subspace K, which contains an open neighborhood around that point. So every compact space is locally compact. Now the converse is not true. That means locally compact spaces need not be compact. Let us consider the real line with usual topology. We know that R is not compact. But for every point X in the real line R, there exists an compact subspace K. X minus epsilon, X plus epsilon closed interval, because we know that closed intervals are compact subsets of real line. So for every point X in R, there exists a compact subspace K, which is a closed interval around X such that this K contains an open neighborhood around X, which is X minus epsilon, X plus epsilon open interval. So for every point X in R, we can find out a compact space K, which is a closed interval around X, which contains an open neighborhood around X, which is the open interval. So R is locally compact. So R is not compact, but R is locally compact. So till now we have studied about three variants of compact spaces, that is limit point compact, sequentially compact and locally compact. Now here we have a result which says that if X is a metrizable space, then the following statements are equivalent. X is compact, X is limit point compact, and X is sequentially compact. That means in a metrizable space, all these three variants of compactness coincides with compact space. One more variant of compactness is countably compact. A topological space X is said to be countably compact if every countable open covering of X contains a finite subcollection that covers X. A space X is said to be countably compact if every countable open covering of X contains a finite subcollection that covers X. From the definition, it is very obvious that every compact space is countably compact. There is one more notion of compactness, which is Lindelöf spaces. A topological space X is said to be Lindelöf if every open covering of X contains a countable subcollection that covers X. So every compact space is also Lindelöf. So this is all about in this lecture. In this lecture, we have studied some variants of compactness, which includes limit point compact, sequentially compact, locally compact, countably compact, and Lindelöf.